Okay, so can you hear me? Okay. So, well, first of all, thanks for the opportunity to give this talk here. I'm going to be talking about joint work with Dennis Amelungsen, who is at Cornell, and Mike McCoy and Joel Tropp from Caltech. And the topic about which I'm going to be talking about is it falls into the general range of ideas that Emmanuel Candes has been talking about. So sparse or simple recovery using convex optimization. So if it was not for Emmanuel's talk, it might be off topic. But if you've seen the earlier this week, then you might well be prepared for the kind of things that I will be presenting. So it's the geometry of phase transitions in convex optimization. So let's start with the basic setting, so the kind of problems that I will be interested in. So the idea is that you want to find a solution to an underdetermined system of equations. So you have less equations than you have unknowns. So there's some information missing, but you know that your solution has a certain structure. So it might be sparse, it might be a matrix of low rank. It could have certain, where's the pointing? Here. Yeah, it could be lying on the on a face of a hypercube. So and there are many more examples. So as a reference, there's the paper. So the general setting is discussed in more detail in a paper by the usual suspects, as Emmanuel Candes would say. And as examples for this convex function here, you might use the one norm, the sum of the absolute values. You might use the infinity norm, or you might use the sum of the singular values, the nuclear norm. I just wrote it the way we have it in the paper with S1, but usually people also write a star there. And the general question I will be asking is, when is the solution of this problem here? Give me the solution x naught that I want to have. So what I'm not going to be talking about is algorithms for solving this. So there are the whole range of methods that you can use. For example, in the case of L1 minimization, this amounts to a linear program. In the case of nuclear norm minimization, you can pose it as a semi-definite program. And there are, in many cases, more specialized algorithms for solving this. So I will not be talking about algorithms for solving this, but just when. So first of all, we actually don't know when a solution of this actually does give me what I want. So this is something that has to be settled first before we start thinking about algorithms for this. Okay. So what has been done so far? So previously, people have shown that in general, if you take A random in some sense, which I'm not going to specify at the moment, then, for example, in the case of L1 minimization, if you minimize the one norm subject to this condition, then you recover a sparse solution to the system of equations, a sparse solution with a number of equations that's roughly up to a logarithmic factor proportional to the sparsity and not to the A-min dimension. So normally I would need D equations, but I can do with something that's here. So that's this general theme has been known as compressed sensing. Also, in the case of minimizing the nuclear norm, there has been a series of works showing similar results. In the case where A would select individual entries, which is matrix completion, or where A is just some random linear transformation. So that's also a series of works there. One phenomenon in this context that has appeared is that if you look at such a system of equations and then you increase the number of observations that you have, so the number of equations, for example, if you start with only one equation here, then you have no chance of recovering anything because you don't get any information. If your matrix has, if you have D equations, so you have a square matrix, then you can, and generically it will be invertible, so you can recover your x naught. And somewhere in between, as you go from 1 to D, somewhere in between there will be a certain threshold that people notice that if you get past this threshold with overwhelming probability for random A, you can recover this solution x naught. And if you're slightly below this threshold, then you have actually no chance of recovering it. So this has been observed, and people have determined pretty good estimates for the location of these thresholds in special cases like L1 minimization or nuclear norm minimization. So there has been the work of Donohoe and Tanner, which is based on previous work by Vershik-Sporishev, and then a different set of ideas by the group of Baba-Kasibi. And they did some pretty good work in trying to estimate the location of phase transitions in some cases. So just to show you what this might look like in the case of L1 minimization. So I want to solve this problem in order to find a sparse vector. So what I do is I start with any sparse vector. I take a random A, just Gaussian, and I generate a vector B. And then I solve this problem and see if the solution corresponds to x0. And for example, if I have a sparsity of 1/2, if I'm about here, and then again, if I have, say, the number of equations that I have here is just half the ambient dimension, then I'm at this point here and I have really no chance. So blue means that this should be a 0 point. So this means that I have actually no chance that this will recover my sparse vector. But if, for example, I have a sparsity of 0.2 and I have a matrix that has a ratio, say 0.8 to 1, then I'm in this region, then almost always for almost all matrices, well, essentially for all matrices, it will recover my sparse vector. And we have this funny boundary here. And so the main purpose of this talk is really to explain what happens in this boundary. First of all, to explain that this, give a geometric explanation that this boundary actually exists, that you have a sharp transition for very general problems. And then also to show that you can locate the position of these transitions in an easy way, a relatively easy way, very precisely. So the main result would be the following. So again, we look at our setting. We have a solution x0 of ax equals b. M is the number of equations, d the dimension. We have this problem here, minimize a convex function such that ax equals b. And then the theorem is that for any probability tolerance that we choose, any small eta, then what happens with probability greater than or equal 1 minus eta, we have the following. If the number of equations is slightly above some parameter that we associate to f and x0, which we call the statistical dimension, and which I will explain in detail later in the talk. If I'm slightly above this parameter here, then I succeed with overwhelming probability. If I'm slightly below this parameter, and I have a transition width of square root of d here, then I succeed with extremely low probability. So this and this quantity here, this parameter, it can be very, it's actually a small constant, essentially. Okay. So let's see how this corresponds with the experiment. So if you take this function that we call the statistical dimension and you plot it, this is in yellow, this is the yellow curve in the middle. So this is the case of L1 minimization, finding a sparse vector. This is the case of nuclear norm minimization, finding a low-rank matrix. Then here you see that this curves, that in theory, the statistical dimension, it corresponds exactly to the position of the phase transitions, and it's computable. Okay. So just as a comment, I'm not going to go into this part in more detail, but if you remember from Emmanuel's talk, he was also talking about problems of separating a low-rank matrix from a sparse matrix or something from. So we can essentially also deal with this case. So rather than finding a solution to a system of equation, we want to separate a signal into two incoherent components. And we can also formulate this as a convex, minimizing a convex function subject to some constraints. And similarly, we can associate to these two convex functions then, which kind of try to capture the different types of structures in my two signals, x naught and y naught. We can also associate statistical dimensions to them, and then we have the result that if the statistical dimensions add up to more or less than the ambient dimension, then I have success or failure with high probability. But so I don't have time to talk about this setting, so for simplicity, I will restrict to what I've been saying before. Okay, why is this the case? So in order to define the statistical dimension, I will have to first of all translate this into a geometric problem. So this problem minimizing fx such that ax equals b has x naught as unique solution if and only if some geometric condition is satisfied. So this is easy to show. So I want the kernel of A, the null space, should have an only trivial intersection with the descent cone of my function f. So and the descent cone is the cone of all directions. If I start at x naught, it's the cone of all directions in which my function is non-increasing. So and under some mild conditions, which I'm not going to into, this corresponds also to the polar of the cone spanned by the subdifferential. So I would have to assume that this is a compact non-empty set that does not contain the origin, but I'm skipping details. I'm just writing this here because in many cases it's easier to have we have at hand a formula for the subdifferential. So we can use this then to compute the statistical dimension of this. So similar condition also for the mixing problems. And now that we have this cone, let's look at some examples of what this descent cone would look like, because we will actually be working with this. So in the case where x naught is a sparse vector, and my function f is the one norm, then so one can, by drawing pictures, one can verify that the subdifferential of the one norm at this point x corresponds to a face of a unit cube. So you have an explicit description of this. Similarly, if x naught is on the S face of a hypercube and I use the infinity norm, then this is obvious. I mean, if you're on a face of a cube, then the descent directions are just an orthant direct sum with a linear space. And there's also a formula for a rank R matrix. So in this case, you can also write an explicit formula. So this formula holds when x naught is diagonal. If it's not diagonal, you write this down in terms of the singular value decomposition. So, but my point here is that you can have explicit descriptions of descent cones for many cases of interest. Okay. So we have this condition, this geometric condition for recovery. We have explicit descriptions for the descent cones. So now we define the statistical dimension of such a descent cone. Okay, so first of all, we define the statistical dimension for any closed convex cone as the expected squared length of the projection of a Gaussian vector. So I take a random vector, I throw it at my cone, then I look at the length, the square root of the length, and then I take the expected value of that, and that's what we call the statistical dimension. It might have appeared under different names in different contexts, but the important thing about this, okay, in the case of a convex regularizer, we just drop the d here, and so just to avoid notation. And the important thing is that it's a direct generalization of the dimension of a linear space. So if you take a linear space, so you throw a Gaussian on it, you take the expected square length, you get exactly the dimension of the lower. You could actually define the dimension of a subspace in this way by throwing Gaussians at it and looking at the expected length. So this is also closely related to a concept that has been studied quite a bit in this setting that's called the Gaussian width. So it actually differs from the Gaussian width by 1, from the squared Gaussian width. But and now let's look at some properties of this. First of all, you can formulate it in terms of a spherical random variable. This is sometimes at times useful. It's rotationally invariant because Gaussians are rotationally invariant. For a subspace, it's equivalent to the dimension. It satisfies all the properties that you would expect of a dimension. So for example, if you have a cone and you have the polar cone, then the statistical dimensions add up to the dimension of the ambient cone, which is just what you would have for linear subspaces with the orthogonal complement. So it behaves nicely under direct products, the way a dimension would. In particular, it's invariant under embedding. It's monotone, so it's just like a dimension generalized to closed convex cones. And let's look at some examples. Well, this one we have seen before. If you take the orthant, or in fact any self-dual cone, you get statistical dimension of d divided by 2. In particular, positive semi-definite matrices. You can also calculate this for the ice cream cones, for the spherical cones. So this is approximately d times the sine square of alpha. You could also look at cones like this one here, x1 smaller than and so on, xd. In this case, you get an expression that is rather small compared to the ambient dimension. So this calculation is not so obvious, but and you can try to do it for many different cones. But so what is one property that we have seen is still missing? So what is one important property of the dimension of linear spaces? And that property is that that two linear spaces, they intersect always if their dimensions add up to more than the ambient dimension, and they almost surely don't intersect, like two lines, if sum of their dimension is smaller. So it turns out that the statistical dimension has a very similar property for cones, but this is a probabilistic property. That's and in fact, the theorem is that if you take two cones and you rotate one randomly, then with very high probability they will not intersect non-trivially if and only if if the sum of their statistical dimensions is slightly smaller than the ambient dimension, then they, with very high probability, they will not intersect. And if the statistical dimension is higher, then they will intersect with very high probability. So this is rather non-intuitive, because if you think of cones, they don't look like linear subspaces. So why should two cones almost always or almost never intersect? But this is what happens in high dimensions. So in high dimensions, cones don't look like we expect cones to look like. And so essentially, this means that in high dimensions, probabilistically, if you are willing to accept terms like with high probability or with low probability, you can treat cones like linear subspaces. So what this means is that a homogeneous convex feasibility problem is solvable with overwhelming probability or not solvable with overwhelming probability if depending on whether statistical dimensions add up or not. So if you apply this to a descent cone, and as a second cone you take for the null space of your matrix A, then you get immediately the theorem I've been talking about before. Okay. So yeah, just to summarize again, here you have what you have for linear subspaces. Here is what you have for cones with high probability. Okay. So half space would have, well, so you can calculate it as a, yeah. So yeah, you can decompose it, and then you can, yeah. So it's like so you have a that's right. You have a space and a line, and then you so you have d minus 1 in that case, or so. D minus one half. Yeah, d minus 1 plus 1/2, because a array has statistical dimension 1/2. Okay, so this follows from. So this is the nice thing about these properties. So you can actually add up, so you have all these different rules that you can use to compose, to calculate the statistical dimension. And for example, for the Gaussian width, much of these equalities would be inequalities. So. Okay, so now we have these properties. Let me just, since we have the statistical dimension, let me just mention quickly, I'm not going to go into this in detail, that we can actually compute this statistical dimension for also other cases of interest. Not so far, I've shown you some toy examples, but the cones of interest would be the descent cone of the one norm, or it would be the descent cone of the nuclear norm. So it turns out that this can be, statistical dimension is very well approximated by this function here, And approximating it by this function is actually a trick that has already been used by in earlier work in the case of L1 minimization by Stoinich implicitly, even though I'm not aware that he proved that these are actually close. So these were bounds. And this function here, this is something. So you take the squared distance of a random vector to a dilated subdifferential. So you actually don't have to worry about details, but this is something that you can find expressions for in many cases of interest. I mean, this has also been bounded in the work by Venkat and Ben and Pablo and so. And there's also a relation to convex denoising that was conjectured by Donoghue and Montanari, and which is being proved in this work also. Okay, so let's look at, okay, here's what I just said, that in many cases of interest, like the L1 norm, you can have asymptotic formulas for the statistical dimension. Similarly, in the case of the nuclear norm, you can find a formula in terms of random matrix theory. And in the case of the hypercube, this is very trivial. Well, this is easy. This is related to what I just saw. This is an orthant times a linear space, so you can actually find the statistical dimension explicitly here. And here is the coincidence with experiments. So here you see these experimental phase transitions for 3 different kinds of recovery problems. And here you see the location of the statistical dimension. So this matches up pretty nicely. And we have a transition region here that is also of the order of magnitude that is being predicted. Okay, now let me quickly say how this is derived in the last 5 minutes, because this is so there's quite a nice theory behind this. And essentially this is by means of spherical intrinsic volumes. Okay, so if you take a polyhedral cone, it decomposes into its faces here, and then the spherical intrinsic volumes for the polyhedral cone would be defined as the probability. For example, the kth one would be the probability that if I project my random vector to my cone, that it falls on a k-dimensional face. For example, this would be V2c, because any point here is in the interior. Here, points here get projected to the one-dimensional face, and here to 0-dimensional. So you could, in a sense, say that Vk is, if Vk is 0.15, you could say that the cone is 15% k-dimensional or so. And then you have this definition of the intrinsic volume. So they form a discrete probability distribution, V0 to Vn, Vd, our case. And you can extend this by several to also non-polyhedral cones. So either by approximation or by some cube formula. And then here are some examples of what this would look like. If you take the orthant, so you can actually work out that the intrinsic volumes take this form, like a binomial distribution. If you take a point and you throw them at the orthant, then that's the probability that they will land on a k-dimensional face. Then for second-order cones, you can also work out these kind of binomial probabilities. So that involves a bit more work, but this can also be done. And implicitly, this for the descent cones of the L1 ball, and so these have been implicitly asymptotics for these intrinsic volumes have been computed in the work by Donoghue and Vershik and Sporishev. So they formulated different. They formulated in terms of counting phases of projected polytopes, but in a dual way. But if you look at it, they actually compute asymptotics of the intrinsic volumes, and there are also integral representations of and this work, I have the impression, is not quite finished yet in the work by Amelungsen and Birgisser for the semi-definite cone. But one important point is that these intrinsic volumes, they give you the probability that a cone does intersect a randomly rotated subspace. So this probability is given precisely by, in terms of this discrete probability distribution of intrinsic volumes. So actually you have the more general formula here that a cone intersects another randomly rotated cone in terms of these intrinsic volumes. But I will now focus more on this thing. So you have a tail of a discrete probability distribution that gives you the probability that I want, actually. Now, and this is the really interesting thing. So you can actually do two things. So this is what you want. So you can actually compute these values here and then see what happens. Or you can do something different. Is like if you flip coins, so you don't compute to know what happens if you flip it 1,000,000 times. You don't have to compute asymptotics of a binomial distribution. You just take the mean, and you have a measure concentration. So you have the result that, or the law of large numbers, whatever, and that tells you that the result will be about concentrated. And you can try to do something similar for these intrinsic volumes, since they are discrete probability distribution. So you can show that this distribution is concentrated around its mean. But now it happens that this mean is precisely the statistical dimension. So you don't have to worry about computing individual intrinsic volumes to get this probability. So to show that with high probability these intersect or don't intersect, it's enough to compute the mean here and to show some large deviation result or something. So this would be the main theorem here. So it gives that the statistical dimension is precisely the expected value of the distribution with the spherical intrinsic volumes, and also that the probability that this deviates from its mean by more than lambda is bounded by some exponent here, which is, so you could say that for small lambda this is more like a normal decay, and for large this is exponential. Yes?
Get this, the cone has to be related to the L1 norm or the nuclear norm, not any norm, right? Because for the L2 norm it wouldn't work, right?
Well, this here holds for any closed convex cone. So
how can you get concentration if you take the cone associated with the L2 norm, for example?
Yes. So
but you don't have a concentration result in this case, right?
Well, I think this holds very general for any closed convex cone. I mean, so it doesn't need any particular assumptions here. So.
But that would imply concentration,
yes.
The phase transition?
Well, yes, this implies, so first of all, it implies concentration for this probability here. So because you can look at this as essentially the tail of a discrete distribution. So this sum will be either 1 or either 0, depending on where you start counting your index. And then, so I think we can discuss this maybe afterwards. We'll actually have to leave out. Yeah, but we can discuss this. Yeah, no, sorry, but I just have to quickly get to the end of the argument. I mean, why this is true, and this is because of the spherical Steiner formula, which is a tube formula. So it gives you. So what I have here is the probability that if I project a spherical point to my cone, that it will lie above a certain level. So this is the probability that I'm within a certain neighborhood of my cone. So this is a tube formula. So on this side, I have this probability, and on this side here, I have the a combination of my intrinsic volumes. So and the point is, if you look at these, so these are the probability that if I project my point to a k-dimensional subspace, that it will be above a certain value. And these here behave a bit like step functions. So they're close to 0 or close to 1. Depending on where I am. So what I have here, it resembles more or less a tail of my distribution here. So you can describe these in terms of beta functions and plot them. On the other hand, by measure concentration on the sphere, what I have here is approximately close to 0 or 1, depending on whether this is greater than the expected value of this, which is the statistical dimension, or smaller than the expected value. So in other words, I have that this tail will be close to 1 or 0, depending on whether my epsilon d is greater or smaller than the statistical dimension. So this is the rough idea. I mean, implementing this actually uses some measure concentration technology, some log-Sobolev inequalities and things. But this is the rough idea. I mean, implementing it is not as easy, but this looks actually embarrassingly simple. So, okay, here just a quick summary of what I said, that you can describe the probability of recovery by the probability of subspaces intersecting cones, and then so these probabilities are given by intrinsic volumes. They concentrate, and this leads to the fact that cones behave in high dimensions of intersection behavior. And here are some open problems still, but I think I don't have time to talk about them in detail. There are some theoretical questions involving the spherical intrinsic volumes, also the question of universality. Does this happen in general? And here are some references. So this is the work I was talking about. This is a work that appeared about the same time and that it kind of complements what we do. Here's, if you're interested in the intrinsic volumes of the semi-definite cone, this is the place to look into. And this is the paper that describes the setting that we are actually working in. Okay, thank you very much. And